This is Mr. Bullins in a series of 4 videos, all talking about motion graphs. We will have 2 videos that talk about distance and time graphs. We're going to have 2 videos that deal with the speed and time graphs. And you may notice already that some of these graphs, such as this one and this one, look very similar to graphs up here. But when you really start to pay attention to what each of these mean, you'll notice that the difference in the speed time graphs and the distance time graphs is that they have completely opposite meanings. So that is something very important. You need to make sure that you notice on the quizzes and tests and anytime you're working with the motion graphs what type of motion graph we are dealing with. And for today, for our first video, we're going to look at speed time graphs. Before we get into the actual speed time graphs, I want to introduce a little bit of what the different parts of a graph are. And we've seen these types of graphs in morning work since the first week of school. What we haven't talked about is this vertical area is your y-axis. The horizontal axis down here is your x-axis. Most of the time, your speed for these types of graphs will be on the y-axis. I will not be giving any to you that are any different than that. And on your x-axis will be your time. Your starting point, because you have to have a starting point, is your origin, is where things can start from. So just remember where your origin is. This is where you would be starting from. Not only are we going to look at and interpret data, we're actually going to plot the data into the graphs as well. The number one and most important thing for you to pay attention to when you get to these graphs, I want you to stop and I want you to first look right here on the y-axis and notice what type of graph this is and circle the word. It will either be speed or it will be distance. And for this video, we're focusing on a speed time graph. That is a very important distinction to remember. Our speed, if you remember, is going to be on our y-axis. So everything that we plot from here in this column will be in our y-axis. Time is our x-axis. And everything that we plot in time will be here. Now, we've talked about it in the ways to plot things because people can get this confused. Is you almost pretend like this is a house. And in order to get in the house and go anywhere in the house, you have to go in the front door, which is our origin. I'm going to go in one spot, which would be here, and I'm going to go up 5 steps. 1, 2, 3, 4, and 5. I'm going to stop there. Now, that is how I plot this data right here. I want to go back and plot this data. So obviously I'm going to go in 2 on the x, there's to here, but I'm going to go up 5. 1, 2, 3, 4, 5. And I'm going to continue that process with my entire set of data that is located over here in this table. And this should look very familiar to you. We've done a lot of this in morning work. And at 6, the object is still at 5. Now I can take a line and connect all my dots and go across. Now, what is this actually saying? Well, this is saying that someone took an object and decided they wanted to measure the speed of that object. And at 1 minute, the object was going 5 miles an hour. They measured it again a minute later. The object was still going 5 miles an hour. 3 minutes later, 5 miles an hour. 4 minutes later, 5 miles an hour. Even 6 minutes later, this object is still moving 5 miles an hour. There has been no change in the speed. Therefore, we call that constant speed. Constant speed. And if we take a look back, we notice that this graph here shows us that it's constant speed. And one thing to take note of is you may see graphs like this with none of the grid marks behind. It could just be blank, but if it tells you that, again, speed and time, I know that the speed doesn't change on this straight line because this line is horizontal and it's not going in a vertical motion, so there is no acceleration of this car whatsoever. It's a constant speed. Very easy to plot, very easy to read, and honestly, if you take your time and memorize that this is a speed time graph and think about the data, I think that you would also come to the same conclusion that this is a constant speed. Let's graph this. Again, speed is on your y-axis, time is on your x. So we have x and we have y. And remember, we're going to go in the door and up the steps. In the door 1, up the steps 1. In the door 1, up the steps 1. In the door 2, up the steps 2. In the door 2, up the steps 2. Go in the door 3, go up the steps 3. 1, 2, 3, 1, 2, 3. Go in 4, up 4. 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. In 5, up 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And now I'm going to draw my line in. Now, obviously you see here that this is going to be called acceleration. Let's make some sense out of this data. At 1 minute, this object was going 1 mile an hour. At 2 minutes, 2 miles an hour. At 3 minutes, it went 3 miles an hour. At 4 minutes, it went 4 miles an hour. You can obviously see that as time goes by, the speed increases. Now, they're not going to call that speeding up in very many questions. They're going to use the word acceleration. We've had that as a vocabulary term. We know what that means from the Newton's laws lessons, but now placing it into a speed time graph, we notice that this is an object that is accelerating. It's getting faster as time goes by. If you can get faster, obviously you can get slower, and they're not going to use the word slower. But let's watch what this object does. Someone measured at 1 minute and realized that this object was going 8 miles an hour. I will label my axis. I will circle speed just to remind myself that this is a speed time graph. So at 1 minute, this object was going 8 miles an hour. At 1, 2, 3, 4, 5, 6, 7, 8. At 2 minutes, the object was going 6 miles an hour. So I'll go 1, 2, 1, 2, 3, 4, 5, 6. At 3 minutes, the object was going 4 miles an hour. 1, 2, 3, 1, 2, 3, 4. At 4 minutes, it was going 2 miles an hour. 1, 2, 3, 4, 1, 2. And at 5 minutes, it was going 0 miles an hour. 1, 2, 3, 4, 5. How many steps am I going up? 0. So my dot would actually be on that bottom line. If I draw my line in here, I will realize that this object, according to this, is decelerating, and we can both easily see that it was going 8 miles an hour, 6 miles an hour, 4 miles an hour, 2 miles an hour, 0 miles an hour. We know we call that slowing down, but we will now use the term deceleration. Deceleration means the opposite of acceleration, which is going to be slowing down, and we're going to call that deceleration. Okay, and in a massive time warp fashion here, we've jumped to a completely different screen. Keep those notes that you've taken and that sheet that you have about speed time graphs. They're going to be very important. And you'll notice that I say here, remember, it is very important to always look at the graph to determine if it's speed or time or distance and time. And all of these, because we're practicing today, are going to be speed time graphs. Our first example says that Gianna studied the motion of the graph below. She says it is at rest. Is she correct? If not, what was her mistake? Now, I'm going to tell you the first thing you're going to do is you're going to check this to see if it's a speed time or a distance time. And I know that it's a speed time graph. Now, if I look back at my speed time graphs, I realize that when I see a straight line, it is constant speed. I already know that she's wrong, so I think her big mistake was probably comparing it to this one. Yes, it looks exactly the same, but this is a distance time graph, and that is a very, very common mistake to make. So I would not agree with Gianna. Gianna did not do the work that was needed. If she were to put some numbers in here, 1, 2, again, not easy to write with this thing, 3, 4, 5, and we call that 6. As time increases, the speed of this object remains constant. So Gianna made a very, very common mistake, a very easy thing to do, but if you take that little extra time to notice the type of graph it is and you study the 7 graphs, you should do very well with those. James looked at the motion graph below and determined that the object was moving up a hill. Is he correct? Again, another very common misconception. Yes, this looks like James is going up a hill. I would agree with that in a lot of ways, except I take my time and I think to myself, this is a speed time graph. If I put those numbers in again, I notice that at different time intervals, at 1 second, it seemed like this object was going about 1 mile an hour. At 2, 2. At 3, 3. And at 4, 4. It seems like as time goes by, this object is increasing in its speed. It's speeding up. We don't say speeding up anymore. We're going to call this acceleration. This is accelerating. I go back to my chart and I notice that this is accelerating. Even if you get this confused with a distance time graph, the answer is never going up a hill. This is not a hill. It does not represent a hill. It either represents distance going up or speed going up. Please do not make that very common error. Taylor was describing the graph below to her teacher. She says the object is decelerating. You need to know what decelerating is. Hopefully you remember, and you can write in your notes, that decelerating means slow down. That way you can kind of put that in your own terms. What are your thoughts? How would you defend your reasoning? Well, if Taylor was smart, she could, number one, say this is a speed time graph. Very important thing to do. If I start at my 0, 1, 2, 3, 4, 5, and then I say 1, 2, 3, 4, 5. I notice that at 1, this object seems to be going about 4.5 miles an hour. At 2, it's going about 3.5. At 3, 2.5. At 4, 1.5. And at 5, it's going 0. This object is indeed decelerating. It is slowing down, and I would agree with everything that Taylor says. That is the first round of videos. This is practice and the introduction video to speed time graphs.